Now let us solve another problem regarding this natural convection. I want you to read the problem first, pause this video, and go back here after you've understood the problem. So you might be thinking, this problem is an example of a condensation problem, probably because you've read that there's this steam that is condensing along the horizontal pipe. But if we would something like give the conditions here, we can imagine this pipe, and then there's this steam here that's slowly condensing, and then it is exposed. This pipe is exposed to the environment, which is the air. So since in this case the material is exposed to air, we cannot still consider this as something like a condensation or heat transfer with a change of phase, simply because the steam is not the one that is encapsulating this material. It's not what is at the surrounding, but the air is. That's why when we talk about this condensation and boiling, we have to understand that the vapor, or say the liquid, should be the one that is on the outside of the material. And when we talk about this condensation, it has to be that this vapor on the outside is condensing in a way that it will produce some dropwise condensation or film condensation. And in this case, it's the opposite. The steam is on the inside and air is on the outside. And particularly what the role of this steam is that it is used to maintain the temperature on the surface, not in a way that this steam would condense because the temperature on the inside is lower. It's not something like that. It's the opposite. So in this case, we're not considering something like a condensation or change of phase, but this is still the normal natural convection of on the external of the material. So still we'll be using the same equation as what we've did before. But before that, we need to check on the condition first. And we have here the temperature of the surface, which is 120 degrees Celsius, and then the temperature of our surrounding, that is 20 degrees Celsius. We also have the diameter, which is 7.5 centimeter, and of course the total heating, so that's 29.3 kilowatts. And the question is the length of the pipe, so we need to find L. And remember, our working equation would always be this: Q is equal to AH and then TS minus TE, wherein this A would translate to our area, that is pi, and then dl, and then H, which is the convective heat transfer coefficient, and this is Q. So if we need L, we can divide all of these, and then we get Q over pi d, and then H, and then TS minus TE. So we've got no problem with Q since it's already given. Then the diameter again, then pi, and also this temperature gradient. So we just need to find our H, and we'll be taking that from our expression of the Nusselt number for our horizontal pipe. So remember, this is also a horizontal pipe, so we'll be using the same expression for Nusselt number. And to do this, we need to find the Rayleigh numbers and the Prandtl number. So I'll be writing the equation again, or the working equation that we need to find H. So that is the Nusselt number is equal to So this is the expression of Nusselt number, and this is equal to the convective heat transfer coefficient multiplied with diameter and then divided by the thermal conductivity. Now, you don't have to memorize this equation because it's already written in your Paris handbook. So now that I've already written the equation, I need to find all of these, the Rayleigh's number and the Prandtl number. And remember, the Rayleigh number is actually equal to beta delta T and then G x cubed and then density squared, and then specific heat capacity, and then divided by mu, and then K. So all of these will be evaluated at the film temperature. Prandtl number is, on the other hand, equal to Cp and then mu over K. You already know this, the momentum diffusivity over the thermal diffusivity. The Rayleigh number relates the buoyancy forces with these capillary forces or the surface tension. Now let's find the film temperature. So it's just the average of the surface and then the environment temperature. So that's Ts plus Te over 2. So that's equal to 120 and 20 degrees Celsius. So divided by 2, this is equal to 70 degrees Celsius, and that is equal to 343.15 Kelvin. So this is our film temperature. We'll be evaluating all of the properties of the air, because that's our liquid on the outside, the fluid on the outside. So that is our point of reference in this case. So it's not the steam, it's not the condensed steam, but it is the air, since it is the one that is in contact with our pipe on the outside. So with this, let's try to have all the values, and again, you'll be using your Paris handbook. So from the Paris handbook, you could see that there's a lot of values here. If we would that you already know this, so let's go to the thermodynamic properties of air, and I've done this before, so you can also go ahead and do it. So I have here thermodynamic properties of air, water. Okay, so this one. Okay, and you can do your own interpolation. So that's another double interpolation since it's 343.15. Remember, the saturated property stops at 132.3 Kelvin. So any property that is above that will be single phase properties, and we need to find the temperature and the properties at that single phase property of our air. And upon doing that, let me just write all the data I have pre-interpolated. So at 343.15, which is at 0.1 megapascal, so the values for the density is 1.0625. That's in kilograms per cubic meter. And then I also have the specific heat capacity, that is 1010.2043, and the unit is actually in joule per kilogram Kelvin. I also have the thermal conductivity, which is 0.0287, and the unit is in watts per meter Kelvin. And finally, I also have the viscosity, which is 2.0382 times 10 to the negative 5, and the unit is actually Pascal second. So I've already done this interpolation, so check it if you will be getting the same answers. And since this is a double interpolation, we need to find as well the values at 1 megapascal. So the density would be 10.6439, same unit, and then the specific heat capacity is 1022.3227, same unit, and then we have 0.0296 for thermal conductivity, and we have 2.0507 times 10 to the negative 5 pascal second for our dynamic viscosity. Now, since I need a value of this at around 0.101325 megapascal, since this temperature here is actually at the ambient air temperature, so we would usually refer to that as being at a normal temperature, that's 1 atmosphere. So this is the equivalent in megapascal. So interpolate in between that and you will be getting these values. So we could just say that these values are already at the film temperature, or I mean film condition. So the density is actually equal to 1.0766, and you can check your answers. If your answer is very far from the values of zero point 0.1, then you might have been wrong. I mean, you have interpolated incorrectly, because remember, this 0.11325 is very close to zero point 0.1. So it's logical to think that the units will be very close to these values we've already obtained. Then the next one would be specific heat capacity. So we have 1010.2221, and then that's joule per kilogram Kelvin. So you might be wondering why this CP is very high. That is very high because the unit is joule per kilogram Kelvin. Remember, the usual unit for our CP is actually kilojoule per kilogram or joule per gram, and that's why the values for, let's say, water, if you can remember, that's 4.184, but that's joule per gram Kelvin. But if you would be using this joule per kilogram, that would be like 4,000, around 4,000. So let's move on with our thermal conductivity at the film temperature. So at the film temperature, the value of our thermal conductivity is 0.0287, and the unit is watt per meter Kelvin. So as you can see, it's the same as for 0.1 megapascal. There's not much of difference, since the value here is quite close, and as you can see, there's no large difference between these two values here. And then our dynamic viscosity at the film, that is equal to 2.0382 times 10 to the negative 5, and it's almost the same for 0.1. Though if you would extend the decimals, then you'll be getting a different value here, but since we're only using 4 decimal places, so it's logical to have the same values. And then let's try calculating our Prandtl number first, since it's a lot easier. So that's Cp mu over K, so that's 110.2221, and then our viscosity is 2.0382 times 10 to the negative 5, and then let's divide it by K. So sometimes you don't have to write all the units, for as long as in the given you have already the units that are consistent with the SI notation, or SI units. So the Prandtl number upon computation would be 0.7174. That's dimensionless. Now the next thing that we need to do is to find the Rayleigh number. So the Rayleigh number is this one. It's beta delta G, delta T G x cubed density squared Cp. And remember, beta here is the one that we solved before, which is beta. Remember, it is the pipe there was actually immersed in a pool. Now in this case, the pipe is exposed to the air, and since air is actually a gas, we can now use beta as if it's the reciprocal of the temperature, and what we'll be using as the temperature is the film temperature. So in this case, beta is actually equal to 1 over the film temperature, which is 343.15 Kelvin. So you don't have to worry about finding the volumetric expansion coefficient for air, because the thing is, you won't be able to find it in the Paris handbook. So that's you should also understand that for gases you should be using 1 over T for beta. If I would be asked, natural convection is a lot easier than forced convection, but what is confusing in this section is that you have to know what fluid you will be evaluating, because sometimes it gets too confusing when you have 2 different fluids, and if the fluids have the values at the Paris handbook, sometimes you will get confused. But remember, when we talk about this natural convection, we're much concerned about the outside environment than the fluid on the inside. Although I'm not saying that the fluid inside has that we disregard that fluid, but the properties of the fluid that is outside of the geometry or the material is the one that we are focusing for natural convection. So anyway, so the Rayleigh number is 1 over 343.15. That's our beta, and then that's we need to find delta T. So delta T is simply the difference between the two temperature. So that's 120 and then 20. Then we also have G, so that's 9.81, and then x cubed. So x cubed here would be the diameter, and the diameter is actually 7.5 centimeter. So we can already convert this to meter. That's 0.075, and then that's cubed. And then we also have density squared. So if we square the density, that's 1.0766, and then squared. And then we also have the last one for the numerator would be our CP. That's 1010.2221. So let's move it somewhere here. So that is 2221. And then we divide this by the the thermal conductivity and the viscosity. That's 2.0382 times 10 to the negative 5. And then the thermal conductivity is 0.0287. So the Rayleigh number is equal to 2414158.146. That's our dimensionless number for the Rayleigh number. And then we need to substitute this to this equation for the Nusselt. So I don't think I'll be writing it anymore since I've already done that in a previous video. You can just substitute it because that's just substitution. So the Nusselt number that you'll be getting is equal to 18.6980, and that's dimensionless number. This is equal to HT over K, wherein we need to find H, and then the diameter is actually 0.075 meters, and then K is equal to 0.0287. That's watt per meter Kelvin. So by just using your calculator, you'll be getting H, and H is equal to 7.1551 watts per meter squared Kelvin. And this 7 point something value for air, for the convective heat transfer coefficient generated from the air through this tube, is very much common since it's around 7. And if it's liquid, that will be very high for liquids. That's why when we try to solve like the one before it, we had some kind of very high value for H. So let's proceed with the final answer. That's L is equal to Q over something like pi D, and then H, and then that's Ts minus Te. So we substitute the values here, so we get L is equal to, remember, Q. So our Q is 29.3 kilowatts, that's times 10 cubed, and then watts, divided by pi, and then the diameter is 0.075 meters, and then H is given by this that we've solved before, that's 7.1551, that's watt per meter squared Kelvin. And then of course the change in temperature would be the surface in the environment, so 120 degrees Celsius minus 20. So this is our answer for the length. So let's just cancel out some units here so that we can obtain the needed length. So that will be in meters. So that is equal to 173.7964 meters. So this is the length that is required to generate that amount of heat in the problem. So it says here that the total heating required is 29.3 kilowatts, and then the length of the pipe. So to accomplish this kind of heating, you need a length of something like 173 meters, and that's quite a long pipe. But of course, it is understandable since this is we're condensing some steam. The steam is inside the pipe, so you need some kind of a very long pipe just to give you that total required heating. And 29.3 kilowatts is actually a large value. So that's it for the this type of problem. It's almost the same as the previous one. It's just that it gives you an idea on how this condensing steam differs from the change of phase heat transfer, because steam is not actually the one that's on the outside or the environment, it's what on the inside of this pipe. Now this is the last problem I'd like to solve for this topic, and I wanted to read it and understand it and then go back here after you've read the problem. So this problem is actually a different problem than the one that we've solved before, because as you can read here, this vertical tube is exposed to a saturated steam at 180 m. Now, I also wanted to specify that this tube here, I modified your module since I just noticed that the Paris handbook doesn't give you an equation for this for plates, so I had to change it, so now it's a tube and not a plate. Well, sometimes the equation would look the same, but there's some subtle differences that you need to account, so we can't use the equations that we have in Paris handbook just to like solve for this plate, but it's almost like the same. It's just the equation that differs. So anyway, since I've already told you that Paris handbook would be our basis for the equations, and I'm not allowing you to use any kind of equation other than Paris, so even though they're just some equations from McCabe or in Gin-Copley's, we won't be using it since you don't do that in board exams. So that's just purely Paris handbook. So in this case, it's vertical tube. And if we would want to like draw this tube, there's something like this tube, and it's a vertical tube. So the diameter here, so it's the diameter, we have 30 cm. It looks like a tree, so something like this. Let me just use something like this just to make it clear. Okay, that's 30 cm, and then the height of this vertical tube is 1.2 meters. So this pipe being exposed to saturated steam, so that's we would have the saturated pressure of the steam, and then the pressure at saturation is actually equal to 1 atmosphere. So you can actually think of this steam being this liquid being a steam at 1 atmospheric pressure. So the thing is, if you have 180 m, that's the normal pressure that we experience. We actually reach this kind of pressure at saturation for the saturation temperature of 100 degrees Celsius. But you know, it's not that exact. So if you wanted to like just do 100 degrees Celsius, then it is okay. But to be exact, I will not be giving you some kind of 100 degrees Celsius immediately. I'll be taking that again from the Paris handbook just to, you know, make it more accurate. And then what we need here is the heat transfer, so that's Q. And then we also need the mass of steam condensed per hour. So let's just name this as our loading weight rate of loading for our steam. That's W sub F, because that's how the Paris handbook works. So this one, if we would evaluate this condition, that is actually condensation, and we now have this heat transfer with change of phase. And in this case, we have a vertical tube. So we need to find this condensation topic with vertical tube of the Paris handbook so that we can get our working equation. So let's head into chapter 5, since that's the heat and mass transfer. And if you hover it around, you'll be getting to this convection and then this forced, and we're done with that. But as you can see, this natural convection is only restricted to the external flow and then these enclosed spaces. But if you would scroll down, you would see this heat transfer with change of phase. That's what we're talking about here. And you can see here, the start of the discussion is condensation, and then it discusses this condensation coefficients. And I have actually written that in your module, but I realized that I've written something like this dimensional and not this um, not the one that is the nozzle type. So these two are equal, but there are cases when the nozzle type is a lot easier to use than the dimensional one, because this WF, as what I've mentioned before, is something like the flow rate of your steam that is being condensed outside. So to get the flow rate, you just have to like give its equivalent, and then it will be, I mean, more difficult for you to like solve for another value that's not directly given. So for now, I'm thinking of just giving you this equation that we need to use. So it's just the same, and I'll be taking the first one here. That's the 0.943 because it's the vertical tube here. So the nozzle type equation is equal to this, but we have to specify that this nozzle type is considering the length of the pipe, or the length of the tube that is being wetted here. And in this case, that's L, since that's the length of the pipe. So it's no longer D but L. That's it for vertical tube. So we have HL over K here, and then that is equal to this value 0.943. So we have 0.943, and then we have L cubed, and then we have something like density squared G, and then the latent heat of condensation, and we have the thermal conductivity, and then we have this dynamic viscosity, and then the change in temperature. And then this one will be raised to its to the 1/4 degree. So having known this formula or general equation that we need, and then if we will be able to find H from this, then we can actually solve for the heat transfer. And if we will be able to find all of these value, then you can solve for the steam that is condensed per hour. But before that, let's just uh, take a look at this equation. And the only thing that is different here is actually this one, this latent heat of condensation. And I know you've already had your thermodynamics, so I already know that you are quite familiar with some latent heat. So latent heat of blank, that's actually depending on the process. For example, we have latent heat of vaporization. So that's the heat that is needed to convert a certain amount of water into vapor. Now, when we talk about this latent heat of condensation, this is almost the same as the latent heat of vaporization, because that's the same energy that you need in order to like convert a certain amount of liquid to its liquid state. And in that way, the temperature doesn't change. So with that, we need to specify that we will be considering the film temperature for our density, for our viscosity dynamic, and of course for our thermal conductivity. Now for the latent heat of condensation, we will be considering the temperature that is at saturation and not the film, simply because the latent heat of condensation happens at a fixed temperature, that is the temperature of the steam, and not somewhere at the film. I would also like to emphasize again that we use film because we need to account the changes or the effects of the temperature at the properties of the liquid. But when it comes to like condensation, which gives you the fixed fixed temperature, so you need to like use the saturation temperature. So I think we're done with all the necessary preparations. So in this case, let's find all of these values. So what we need here is the density. By the way, this is the acceleration due to gravity, so we don't need to find its constant. This one, and so we have something like 4 physical properties that we need to find. By the way, in your Paris handbook, it's delta T small, but this just translates to something like saturation temperature minus our environment temperature, or you could say that it's the surface temperature, if you might say. So let's solve it. So first, I need to take the film temperature. That is, the film temperature is actually equal to the saturation temperature plus the environment or the surface divided by 2. And in this case, since I am given with the atmospheric pressure, which is the saturation pressure. I just need to go back to the Paris handbook and locate the saturation temperature. So I'll be taking the saturated properties here, and that's the actually the very first I mean table that you'll see are actually the saturated properties already. So if you have something like this actually the saturated properties. So if you can evaluate something around point 0 around this, because as you can see here, the pressure here is 0.0905 to 0.12885. So at the middle of around this section, we have something like 0.11325, which is our pressure at 1 atm. But along this line would be around 100 degrees Celsius. That's, I mean, that should be expected, but it's not really like that exact 100 degrees Celsius. So with that, I still need to interpolate in between that. So upon interpolation in between this by taking 101,325, so the saturation temperature is actually equal to around 99.6661 degrees Celsius. So that's very close to 100 degrees Celsius. And if you would take the average of that, that's 99.6661 and then added with 20. So divided by 2, it gives us a film temperature of 89. So, sorry, it's 80 degrees Celsius. So, taking the average would be 89.8331 degrees Celsius, and the film temperature at Kelvin would be 362.9831 Kelvin. So now that we have already obtained the film temperature, we're gonna evaluate all of these at the film temperature. So let's take a look at the Paris handbook again and check on where is this film temperature. That is 362, so it's around here, just one step higher. So we'll be evaluating all of these. What are the things that we need here again? We have the density, the latent heat of vaporization, and then of course this thermoconductivity and viscosity. But remember, this the latent heat would be evaluated not at the film but at the saturation temperature. So you can interpolate in between these values to get all of this, and then you must be getting these values. So we have here the density is equal to 964.5397. I'm just using 18 as molecular weight. And then we have here, of course, the G would be 9.81, that's meter per second squared. And then we have the latent heat of vaporization at the saturation temperature. So I've already evaluated that. That's 2250 6.6136. That's kilojoule per kilogram. Now, if we need it to have in its MKS, so we will have 2256 and then 613.561. That's joule per kilogram. And then we have the film thermal conductivity, so that's 0.675 and then watts per meter Kelvin. We also have the dynamic viscosity at the film, so that's 3.1574 times 10 to the negative 4, that's Pascal second. And then of course this delta T would be the difference in temperature. So we already have this value, and now let's try to substitute this with our equation. So we have HL over K, that is equal to So HL over K is equal to 9052.1413, and this is equal to H times 1.2 meters divided by K, so that's 0.675 watts per meter Kelvin. So the value of H is actually equal to 5,091.88295. That's watt per meter squared Kelvin. So it's not the end of the computation, that's just H. And I would also like to emphasize this lambda here, or latent heat of vapor of condensation. Just an information, or if you forgot it. So once you've obtained the value of the enthalpy at this portion, which is the liquid, you also have to take the enthalpy at the same temperature at the vapor phase and then subtract it so that you would get the latent heat of condensation. So using this, enthalpy at the liquid would give you a wrong answer, since the phase there is actually a mixture of some kind of liquid and vapor. And using this vapor phase only for the latent heat of of condensation would also give you a wrong answer, since it's not a pure, it's not pure like steam, but it's a mixture of the two of them. So you need to subtract it. Okay, so if you're not getting the same answer for the latent heat, then probably you haven't subtracted the two values. So in this case, let's move on with our Q, since that's the one that we need. So Q is equal to AH and then TS minus TE. So Q is equal to the area, and the area is actually the area of the rectangle, so that's 1.2 meter. I mean, the area of our pipe, so that's D, the L, which is the length, and then pi, and then of course this 30 centimeter, which is the diameter, so that's 30 cm divided by 100, just to make this in meters. So that's cm per meter. And then we have this H, that's 5091.8295, that's watts per meter squared Kelvin. And then the difference between the temperature, that's 99.6661, and then 80 degrees Celsius. So Q is equal to, now Q is equal to 113,251.6321 watts. And if we're asked to find, this one is one of the answers, and if we're asked to find the mass flow rate of our condensate, that's WF. So how do we find this? Okay, so there are a lot of ways to find this mass flow rate. If you would think of it as something like this, mass is equal to density is equal to mass over volume, so that would be something like density times this volume, and then derive from this using this kind of density, and then the volumetric flow rate will be the velocity of the fluid times the area, and then take on all of these values and then relate it to the Reynolds number. That could be something like a solution. But the change in the temperature of the fluid inside would give something like the energy balance in between this condensation and this change of temperature of the fluid that's inside. So in that case, if you would take the the flow rate of this condensate and then multiply that with the latent heat of vaporization, you're actually taking the equivalent of the heat that you have. So the easiest way to find WF is simply divide this Q by the latent heat of vaporization. So in this case, what we'll be getting is 113,251.6321, that's watts, and then divide this by the latent heat of condensation, so that is this one, 225,6613.561. And that's the same concept of what we do in evaporation. That's just something like this, the steam value, and then the latent heat of vaporization of the steam. So we have something like 2200, I mean 225,613.561, that is in joule per kilogram. So since this watts is joule per second, what we'll be getting here is the value of the flow rate in kilograms per second. So our flow rate in kilograms per second is 0.0502, that's kilogram per second. But if we need this based on the problem in terms of kilograms per hour, you just need to multiply this to 3600. So the value of our condensate that flows probably downward from the external would be 180.6716 kilograms per hour, and that's quite a lot of condensate that comes out that you can see probably from the film condensation or dropwise condensation on the external surface of this tube that we have. So that's the total mass of steam condensed per hour. And actually, if it's per hour, then your answer should be around something like 180.6716 kilo, just the kilogram. So now I would also like to tell you about this thing that we did here. We actually used this formula immediately, but on the contrary, I mean, we had to read something from the Paris handbook and see it from here that it says here that when you are using something like this, we need to check on the Reynolds number, and it says here that the Reynolds number should be less than, I don't know if you can say it, but in vertical tubes it says here that the Reynolds number should be less than 2100. Let's zoom, it's somewhere here. It says here that the Reynolds number should be less than 2100. It means that the flow should be laminar, and if the flow is not laminar, then we shouldn't be using this formula. And actually we have assumed that this is laminar flow, so that's one of our assumption that I forgot to mention, because actually the Paris handbook doesn't give you any equation for turbulence, so that's all we can do. We can assume that this is laminar. And to do this, so we have already the laminar flow, and we need to check if we really do have some kind of laminar flow. And remember, the Reynolds number is given by dV rho over mu, and if we would like to relate this dV rho mu with our mass flow rate at WF, we could see that from this equation, the rho V, we could see that rho V is actually equal to the mass flow rate or over area, or this is our WF over the area. So in this manner, if WF over area is equal to rho V, we could say that this one is D times WF over A, and then divided by the viscosity, wherein the area is the area of our diameter, the area of our cross section. So in this case, that's D, and then WF over, this will be pi D squared over 4, and that's mu. So we can cancel out D from this one, and then we'll be getting is 4, and then the mass flow rate of condensate divided by pi D, and then the viscosity, dynamic viscosity. So we need to evaluate this Reynolds number using this formula, and if you would check on that, we have 4, and then WF is actually, this is in kilogram per hour, but we'll be using this one, so that's 0.0502, and then we have pi, and then the diameter is actually 30 cm, so let's divide it with 100, and then our dynamic viscosity is given by this 3.1574 to the negative 4, so that's 3.1574 times 10 to the negative 4. So we need to check on this, and we should have an answer that is in laminar flow. If not, then our assumption is incorrect. So upon solving from this, the value of our Reynolds number is 674.7812, which justifies our assumption that this is less than 2100, and we could say that the flow is laminar. So that's a correct assumption. So had it been greater than 2100, then we have actually an incorrect answer for this since we didn't meet the assumption for this. So that's all for our condensation, and that's all for the natural convection. I've given you 3 cases when there's some kind of confusion that exists in between this condensation and in external flow. Boiling is just the same. You'll just be using a different equation, but the concept is just the same. If the problem says that if you have something like a tube that in which the fluid on the outside starts to like boil, so you'll be using the boiling coefficient, and that happens when you try to like boil something like fluid on the inside. And technically, we're in boiling, sometimes the fluid that is being boiled is on the inside and not on the outside. But if you have something like a material that is very hot, and then you immerse that into certain fluid, then you'll be considering the fluid that is on the outside, because that's our general rule for boiling heat transfer coefficient. So you also don't have any boiling. Don't have any boiling case here. So yeah, that's all. I think you just be applying the same concept for condensation. So thank you, and we're now heading to radiation, which is the last of the heat transfer mechanism.